If I told you to draw a curve, you could probably do it without thinking. But for a computer, it isn't as intuitive. To connect 2 points, a computer needs the equation of the line. And when it's a straight line, that's pretty simple. It's just y equals mx plus b. But the curvier the line, the more complex the math needs to be. That's where splines come in. Today, let's explore spline fitting, starting with what splines are and why they're often the hero you need when polynomials fail, before diving into different types of splines you'll encounter when trying to fit your curve and how the Curve Fitter app in MATLAB makes fitting a spline easy. If your data can be modeled with a single simple curve, a basic polynomial like y equals x squared does the trick. However, there are limits to using a single equation. Using a higher degree polynomial creates a more complex curve that's more likely to overfit your data. Additionally, polynomials of any degree can provide a good fit with the data points you provide, but can diverge once they leave the neighborhood of your dataset. If you know the underlying shape of your data, say exponential decay or a sine wave, a parametric or polynomial may work fine. But if your data is noisy and you need a smooth trend without assuming a specific equation, that's when splines are the right tool. Instead of one overworked polynomial trying to fit a dataset, splines break the data into manageable segments, stitching them together at points called knots. The result is a flexible curve that better fits the data. When working in MATLAB, there are many types of splines, but for today, you'll only want to know about 2. Those are cubic spline interpolation, the overachiever standard bearer of this category. This method requires the curve to pass through every single data point. If you have clean, non-noisy data, cubic spline interpolation has your back. Smoothing spline. Now, this method doesn't force the curve to pass through every point. Smoothing splines try to find a happy medium by staying close to the data points while keeping the overall curve smooth. By adjusting a smoothing parameter, you can change how tightly the spline fits the data. A smoothing parameter of 0 gives you a straight line, while a parameter of 1 makes the spline an interpolator, meaning it's forced to pass through every single data point. When unsure of which method to use, you can try both to see which one gives you the best results. With the Curve Fitter app in MATLAB, you can easily explore both approaches to spline fitting. Let's take a look at a real-world example. Creating mechanical components often requires repeatedly heating and cooling steel to properly temper it and avoid creating brittle metal. In this demo, we're creating gear shafts, and we need to make sure that we're heating and cooling the steel to temperatures in line with industry regulations. Now, the obvious thing to do is to simply put a temperature sensor in the furnace. But it turns out the temperature data our sensor received has a fair bit of noise thanks to problems like EMF drift, air turbulence, and contact resistance. So we need to fit a clean model to our data to account for the noise. Looking at the graph, we can see what the curve should look like. There's a little peak here, and then it climbs to the biggest peak, before decreasing and then increasing again to the second highest peak. And then it decreases with a couple of smaller peaks. But how can we find a model to fit the data? Well, that's where the Curve Fitter app comes in. With the app, all you need to do is select your data, and you can start trying out models. With the polynomial option selected, you have the option to set different degree polynomials based on the data. We can see here that a 5th degree polynomial is still far too smooth, and a 9th degree polynomial, while better, is still missing both of the peaks. Let's try a different method. You can select interpolant and cubic spline to use the cubic interpolating spline. While these points may look like they're joined by straight lines, zooming in reveals the points are in fact plotted along small curves. However, this is obviously overfit. Cubic interpolation does not work well with noisy data. So how about smoothing splines instead? Well, initially, it's hugging the data too closely, but by going into the Fit Options panel, we can change the smoothing parameter. Currently, the parameter is closer to 1. We can see firsthand here that if the parameter is 1, it fits every point. If the parameter is 0, it's a straight line. But going back to the default, we can select smoother or rougher to create a spline that's more or less smooth. By clicking the smoother button a few times, we can get a model that smooths through the noise and captures the underlying trend. Now that we have a spline, we can check how well it fits by looking at the results panel. Or you can inspect the residuals visually by clicking the residuals plot. Because our residuals are well distributed, we can conclude that our curve is well fit. Now that we have our spline, we can export it as a figure, export it to our MATLAB session either as code or to the workspace itself, and export it to Simulink. As you can see, the Curve Fitter app allows you to try and fit different splines with just a few clicks. To recap, The benefit of spline fitting is flexibility, as splines allow us to fit curves that more accurately reflect complex data. And tools like the Curve Fitter app in MATLAB make spline fitting a straightforward process, which means you can get to analysis even faster than before. Check out the links in the description to learn more about spline fitting, spline interpolation, and curve fitting in MATLAB. Thanks for watching, and happy coding!